Hi everyone, welcome back. Today we're going to be talking a little bit about the theory that we need in order to use Laplace transforms. We are going to set up a couple of definitions and then some theorems about uniqueness and existence that are going to help us use Laplace transform methods to solve initial value problems. So to begin with, we need a couple of terms for the function f that we're applying the Laplace transform to. We need to know what it means for such a function to be piecewise continuous and also for it to be exponentially bounded. Those turn out to be the two properties that a function has to have in order to have a Laplace transform. So to begin with, we say that a function is piecewise continuous on an interval 0 to t if it is discontinuous at only a finite number of points. So you can't have infinitely many discontinuities on a particular interval, and at each of those points of discontinuity, the left and right hand limits exist. They don't have to match, and often they won't if a function is discontinuous at a point, but they have to exist. So just to look at a visual of what a piecewise continuous function might look like, so suppose that we have an interval from 0 to t, and we have a function defined here, so it might be piecewise continuous if it looks something like this, and there can be more than one discontinuity. So we would say that this function is piecewise continuous. And we'll often abbreviate that as piecewise, PW continuous. All right, so the idea is that at each of these points of discontinuity, I haven't drawn that particularly well, I guess. Those are supposed to be connected. At each of these points of discontinuity, like here, the limit from the left exists, the limit from the right exists, but they don't match each other, and that's fine. It's fine that they're discontinuous. There are 2 points of discontinuity, so a finite number, so this function is piecewise continuous. Now, if we violate any of those requirements, then we'll get a function that's not piecewise continuous. So we could have infinitely many discontinuities in our interval. That would be a problem. I'm not going to draw that. We could also have points of discontinuity where the limits don't exist. So that could happen, for example, if we have a function that has an asymptote. Right, so maybe it picks up here. All right, so that's one way that things could go wrong. But another way is if the function is oscillating a lot. So one of these, that's another way that our limit could fail to exist. So if the function oscillated back and forth so that the limit didn't exist. So this is not PW continuous. This has 2 points of failure. One where this limit on the right-hand side, this limit doesn't exist. Infinity doesn't count as existing. The limit on the left, I mean. The limit on the right is fine, it exists. The limit at the second point over here, the limit from the left exists, but the limit from the right does not because of oscillation. So that's not piecewise continuous. All right, so back to our definitions. We said that a function is piecewise continuous on the interval from 0 to infinity if it's piecewise continuous on every finite interval. Right? So that kind of function could have infinitely many discontinuities. It just can't have that many on any finite subinterval. All right, so that's piecewise continuity. And then we have this concept of being exponentially bounded. We say that a function is exponentially bounded if there's some constant m and a so that the absolute value of f of t is always less than or equal to m times e to the at. So basically, there is some exponential function, any exponential function at all, that is always on the outside of this function. So basically, this just says that a function cannot grow faster than every exponential function. And if that's the case, we say that the function is exponentially bounded. Why do we care about these things? Well, we have an existence theorem. If a function is piecewise continuous and exponentially bounded on an interval, and so, for example, we're going to use this specific number here, the actual exponential bound, because the value of that exponent a is going to turn out to be important to us. So if a function is piecewise continuous and exponentially bounded, then the Laplace transform, which recall this is the definition of the Laplace transform, the integral from 0 to infinity of f of t e to the minus st dt, this will exist for all s greater than a. So whatever that bounding exponent is, we get existence for that. So we're going to want to find the smallest possible a that makes this work. And in many cases, that's going to be 0, or any number just a little bit bigger than 0. So if a function is piecewise continuous and exponentially bounded, the Laplace transform exists. That's something we're certainly going to want to know about. All right, so here's our graphs. Now, once we know that Laplace transforms exist for some functions, we're going to want to be able to build up a bigger and bigger collection of functions for which they exist as well. So suppose that we do have two functions, f1 and f2, that are piecewise continuous and exponentially bounded so that they have Laplace transforms. Then both any of the linear combinations or any product of these two things is also going to be piecewise continuous and exponentially bounded, right? So if we multiply these together, the discontinuities from both will show up. That's fine. But we will have at most a finite number of them, and the limits will still exist. And the exponential bounds will still happen for any linear combination. We just have to take the bigger of the two functions, basically, and we will get an exponential bound. So that leads us to a theorem that says, if those things are true, which is encapsulated here, if f1 and f2 are piecewise continuous and exponentially bounded on the infinite interval, then, so those are their exponential bounds, then if we take any linear combination of them, so f of t equals c1 f1 plus c2 f2, then this new function is also piecewise continuous and exponentially bounded, and the Laplace transform is just the linear combination of those things. Basically, the Laplace transform is a linear operator on the function space. So we just have to take the Laplace transforms we already know for f1 and f2, and we'll get the Laplace transform of f. And the domain on which this is defined is for s bigger than the maximum of a1 and a2. So these two exponential bounds that we had on the original functions. Great. It also turns out that this works for products. So if g of t is equal to f1 times f2, then g of t is piecewise linear and exponentially bounded on that same interval. And this Laplace transform exists for s1 bigger than a1 plus a2. And you can see why it would be that, because you would be multiplying these two bounds together. You get e to the a1 plus a2 times t. Now, we're not going to write down the formula for that yet. That turns out to be a little bit more complicated than we want to get into right now. But we know that it exists, which is good. All right, so we can expand the world of functions for which we know that Laplace transforms exist. All right, and then finally, recall from last time we had this diagram of how the transform process would work, right? We would start from an original domain and then go over to a transfer domain and then solve the problem and then go back to the original domain solution. That going back process, we need to know that it's unique. Basically, if we figured out something on the transform domain side, we want to know that we can go back to the original side. If there's not a unique way to do that, then we're kind of lost. We'll have a solution on the transform domain side, but we won't know that what the solution in the original side is. We need a lack of ambiguity, right? So it's important. So we don't want that ambiguity. Information would be lost in trying to go backwards. So this whole process would be useless. But thankfully, it's not the case. If two functions have the same Laplace transform, then they are themselves the same function. Basically, there's a one-to-one correspondence between functions and Laplace transforms. And that's what this last theorem tells us. If f1 and f2 are the things we need them to be, then their Laplace transform, and we look at their Laplace transforms, f1, capital F1 and capital F2. If there's some constant a for which f1 of st equals f2 of st for every s bigger than that, then the original functions f1 and f2 must have been equal for all t greater than or equal to 0 at all points where they're both continuous. So unique correspondence between functions and their Laplace transform. So we have f of t can be mapped to f of s in a unique way, right? Just by doing our calculation that defines it. But now we're seeing also that there's a unique way back. It's one-to-one correspondence. So anything we solve in the domain, in the transform domain, will correspond to a solution in the original domain. Okay, so Laplace transforms are unique, or at least as unique as we need them to be. There's a little bit of detail in here about what to do with points of discontinuity and some other stuff, like what if it's only partially matching, but it's enough for us to make things work. So we're ready to do the thing we need to do next. In order to be able to go from this transform domain back to the original domain, we need to know what those correspondences are. What functions have what Laplace transforms. So we're going to begin the process of cataloging, of looking at different functions and seeing what their Laplace transforms are. These are called Laplace pairs. We're going to figure out what those pairs are. That's going to begin next time. So I hope this was informative.